Hello students, welcome you all to the lecture number 5 of our series Oscillation. So today we will discuss about resonance. In the last lecture we discussed about forced vibration, wave equation of forced vibration and its solution. During that derivation we calculated the amplitude of forced vibration also. During that lecture I told you one more thing, that is said to be resonance, where we are getting maximum amplitude. So what is that condition? How it affects our day-to-day life, and what are the different examples we are facing in the day-to-day life due to resonance. We will focus on that topic here in lecture number 5. So let's start the topic. So here you can see the definition of resonance is written. So resonance is what? When the external frequency, that is the frequency of external periodic force, which is also said to be the driving frequency, matches with natural frequency of the body. At that condition, the amplitude will be maximum. So this maximum amplitude condition in forced vibration case is said to be resonance. So it is a special case of forced vibration. We are getting maximum amplitude here. So here you can see it is written the definition, and this is known as resonance, and this is nothing but the extreme case or a special type of forced vibration. So resonance can be mechanical, resonance can be acoustic, that means in sound case also we are finding some resonance. Resonance can be optical, in case of light also we can achieve some resonance condition. Resonance can be electrical, in electric circuit also we can find out resonance. You must have studied that LC oscillation, resonance in LCR circuit also. So that is electrical resonance. I think you remember the expression for amplitude of forced vibration, which was like this: amplitude of the body is equal to F naught divided by omega naught square minus P square whole square plus 4R square P square square root. So this was the expression for amplitude in case of forced vibration, where I think you remember that omega naught is the natural frequency, P is the frequency of the driving force, that is that external periodic force, R is the damping coefficient. So when omega naught equal to P, then we get A max, that is a maximum value. So what will be A max? A max will be F naught, then this part will be 0. This part will be 0 because omega naught is equal to P. So omega naught square minus P square will be 0. Then we are getting only square root of 4R square P square. So if we are getting 4R square P square, then its square root will be 2RP. So this is the expression for maximum amplitude. So at resonance condition, when omega naught equal to P, we are getting this expression for amplitude. So here you can see one more thing. If we decrease, if omega naught is greater than equal to P, when omega naught is greater than equal to P, then we are getting some value here. So denominator value will increase and A will be less. But when omega naught is less than equal to P, then also this is a square root term, so it cannot be negative. So some quantity plus 4R square P square. So again denominator increases. That means the total factor gradually decreases. The only condition is nothing but omega naught equal to P. On either side of that condition, if omega naught is less than P or if omega naught is greater than P, in both cases we will find out that the amplitude of forced vibration will be less as compared to the resonance. For that reason, this is said to be maximum resonance. If you plot a graph like that for amplitude along y-axis, if we plot, and frequency, the driving frequency P along x-axis, then we will find out a graph like this. Then what are the 3 different graph or 4 different graph I am plotting? I will explain each one of it. Somewhere you will get graph like this. So I will explain each one of it. In which condition we are getting the first graph, second graph, third graph and fourth graph. First thing you observe here, this is when omega naught, the condition is omega naught equal to P, right? So this is when P is less than omega naught, P is greater than omega naught. When P is less than omega naught, in that case also we are getting less amplitude as compared to the resonant frequency. Resonant frequency means when omega naught equal to P. When P is greater than omega naught, then also we are getting amplitude which is less than that resonant frequency. So this maximum is said to be resonance frequency condition. So the first one is said to be high damping condition, high damping. This is moderate damping. This is less damping. This is no damping. So if we plot the graph between amplitude along y-axis and frequency, driving frequency along x-axis, then when the external force which is responsible to decrease the energy, that is the damping force, is high, in that case we are getting amplitude this much. If the damping force decreases, that means more energy will be there for vibration, so gradually the amplitude also increases. When there is no damping, in free damping case, we will find out a graph like this. So this graph represents the variation of amplitude of forced vibration with respect to the driving frequency. So maximum, from here you will clearly can see the maximum amplitude you will get at omega naught equal to p. Here also you can see one more thing, on both sides of that resonant frequency the value of amplitude gradually decreases. So that is a term that is said to be sharpness. Sharpness of resonance. Then what is sharpness of resonance? Now on both sides the amplitude fall, so the rate at which amplitude falls on both sides of resonance frequency is said to be sharpness. So rate means how fast the value of amplitude decreases, that defines sharpness. So sharpness of resonance is nothing but the rate at which amplitude falls on both sides of resonant frequency is said to be sharpness of resonance. So let's discuss about some examples we are facing in the day-to-day life due to resonance. So here you can see there are different types of resonance. We discussed mechanical resonance, acoustic resonance, optical resonance, electrical resonance. So we will discuss some of the examples we faced in day-to-day life. So here the first example is Tacoma Narrows Bridge collapse, which occurred in 1940 in USA. So here you can see a bridge was constructed, which was hanging bridge, but when the frequency of the wind matches with the frequency of the bridge, that means resonance happens. Frequency of the wind is the external force and natural frequency of the bridge. When the external frequency matches with natural frequency of the bridge, then it vibrates, suddenly it vibrates with maximum amplitude, and as a result of which it collapsed. You can see this video. See, this was the bridge. See the vibration here. When the wind matches with frequency of the natural frequency of the bridge, then it vibrates or it resonates with maximum amplitude, as a result of which it collapses. From here we confirm that resonance is destructive in nature, but in some example we will find that the resonance is useful in nature. So in day-to-day life, in our life, resonance is destructive as well as constructive. So this type of wind-induced resonance is destructive because it will leads to collapsing of the bridge. There are some more examples also. You can see any type of musical instrument, if you consider like guitar, sitar and all these things, violins, where strings were stretched, strings were there. In that case, when you vibrate that, due to resonance, the vibrating sound wave amplifies. So this is constructive in nature. This is useful. Similarly, radio and TV transmission. In radio and TV, for example, you are considering, for example, any FM. For FM, 104 FM. So we are setting the frequency at 104. That means it resonates with the frequency with which the broadcaster are sending the frequency wave or that wave. When we matches 104, the incoming wave is 104. If we matches the frequency of our radio 104, then suddenly it matches, both the frequency matches, and we are getting amplified sound wave or clear sound wave. That is the example of radio and TV signal where resonance occurs. Similarly, building collapse during earthquakes. Whenever the frequency of the seismic wave, that earthquake matches with frequency of the building, then also it collapses. These are some pictures of Mexico City, which happens in 1985. Similarly here, glass breaking with sound. If high pitch sound or high intensity sound is there, then it will lead to breaking of the glass because the molecules of the glass are resonating with a particular frequency. When frequency of the sound wave matches with that frequency, in that case, it will lead to breaking of the glass. During concert also you must have seen the glass vibrates. Similarly, MRI, magnetic resonance imaging. In magnetic resonance imaging, what happens? The magnetic fields are given. So magnetic field induces resonance with the protons present in our live cells. So whenever resonance appears, then we are getting a clear image. Similarly, microwaves also. In case of microwaves, so microwaves are a particular type of electromagnetic wave. So those waves induces the water molecule. This resonate with the frequency of water molecule, as a result of which it results in heating of the food. So these are some examples of resonance. So resonance can be, always remember, resonance can be useful as well as destructive in nature. Then these are some engineering solutions how to control resonance. If we control the damping, if we control the energy, then we can control the resonance. One is the damping technique. So if we use rubber, foam, viscoelastic layer, in that case what happens? It absorbs the vibrating energy. If it absorbs the vibrating energy, then obviously it will reduce the amplitude. Those are nothing but used in cars, building and bridges. Similarly, tuned mass damper. Nowadays, tuned mass dampers are mainly used in skyscraper. So when the height of the building is very high, then the risk of vibrating the body, vibrating that building with seismic wave and all these things will be very high because of its high structure. So to make it earthquake prone, mainly we are using tuned mass damper, as well as the third case is also used nowadays, tuned mass damper. So what is tuned mass damper? Now in tuned mass damper, a heavy mass is used. For example, this is a building. So what happens? Now tuned mass, a heavy mass is used here. Heavy mass is fixed with some hydraulic points at this point. So what will happen? It will vibrate in the opposite direction of the vibration, as a result of which the total energy will decrease because of in opposite direction. So here are some examples. They are used in bridge, high speed trains to maintain stability. If energy decreases, then damping also decreases, as a result of which the amplitude also decreases. Structural design adjustment. Engineers avoid uniformity in structure. More flexible structures are formed and they are not fixed, they are movable. Whenever some earthquake will be there, they can rotate or they can slightly move at their position. So that will reduce the amount of amplitude, that will reduce the amount of energy, as well as a result of which it will keep the building in shape. So these are the examples how we can reduce resonance. So in this lecture we discuss about what is resonance, how it can be useful as well as destructive in day-to-day life. We discussed about some real life examples also. So whatever real life examples you faced due to resonance, you can let me know in the comment section, and if you have any question you can also ask in the comment section. Thank you.